Hello everyone, my name is Nethiki Navinhara and this is my project pitch for SIT 210 Embedded System Development. My project is called Smart Garden Automation System, which uses embedded system to solve real-world irrigation problems. There are four phrases that I'm going to discuss in this presentation. Problem statement and industry limitations, proposed solutions, and system components and interfaces. So, when it's come to problem statements, manual watering of plants is often inconsistent, leading to overwatering and underwatering. This harms plant health and waste water so much. And while some people use timers, those systems are rigid and don't adapt to soil conditions. More importantly, there's no real-time feedback or remote control, and the sensing and control parts often don't communicate. This is where my solution comes in. Traditional practices rely on manual effort or fixed schedule sprinkles. These are time consuming and inflexible. So high-end smart systems do exist, but they are often expensive. So we can't reach them and hard to customize and don't offer feedback or control integrations. And many systems operate in isolation and they sense but not share data, or they act but don't respond intelligently. My solution consists of two embedded systems that communicate with each other. System A, which is an ESP32 microcontroller, stays in the garden and it reads soil moisture and controls the water pump. And when it comes to system B, which can be a Raspberry or another ESP32, and act as a remote hub or user interface. These two systems communicate over Wi-Fi using MQTT protocol, and system A sends live sensor data and status updates to system B, and system B can send command back and like turning the pump on or off either manually or based on schedule logics. Here's the breakdown of the system. System A includes an ESP32, a soil moisture sensor, and relay module, and a water pump. It also has LED indicators for local feedback. And system B includes a Raspberry Pi, which receives the data and displays it to the user. The MQTT broker handles the messaging between the two systems. Optionally, we can also use the Blink app for mobile control as well. The soil moisture sensor sends analog signals to ESP32, and then the ESP32 controls the relay digitality, and it sends a sensor reading to Raspberry Pi over MQTT using Wi-Fi Nina, and the Pi can send the control commands back over MQTT. Optionally, the Pi can connect to the cloud or Blink app for remote access also. So when it's come to the block diagram, I will explain it. This block diagram shows the full architecture of the project, and the soil sensor connects to ESP32, and the ESP32 controls the relay and the pump. It sends real-time updates via MQTT to the Raspberry Pi, which can show the data on the web interface or app. And the Pi can also send commands back to the ESP32 to control the pump remotely. Next, moving on to the flow diagram. There are few steps in the flow diagram as well. Read soil sensor, send data and active pump, data logging, user commands, adjust pump, So this is the flow diagram that I've created. Here's how the system works step by step. The ESP32 reads the soil moisture level, and if the soil is dry, it turns on the pump and sends the data update to the Raspberry Pi, and the Raspberry Pi logs and displays this data, and the user can send manual commands back from the Pi or app, and the ESP32 adjusts the pump accordingly, and the system loops and continue monitoring in real time. So that's happening in the project. The system interface includes a web dashboard or app to display moisture levels and pump status. You can also control the pump manually from here locally. The ESP32 uses LED to indicate soil status, red for dry and green for moist. This system includes many features aimed at high distinction, real-time two-way communication between devices, watchdog timer, and data filtering for reliability. And MQTT ensures reliable delivery of messages, and the system still works offline if communication with the Raspberry Pi fails. The other thing is the design is escapable. You can add more sensors or pumps. When it comes to benefits and impacts, the system saves water by watering only when it needed, and it improves plant health with consistent moisture levels. You can manage it remotely or even automate it further. It is scalable, modular, and cost effective, and suitable for homes, farms, and education projects. You can use any. There are so many ways to use this because this is affordable. In conclusion, this project solves a practical problem using two communication embedded systems. It combines sensing, automation, and connectivity for smart gardening. It is a solid foundation for future development in smart agriculture also. So thank you for your time and attention. I am happy to answer any question or explain any part in the more detail. Thank you.